Hello everyone, this is our last video for Unit 3, the periodic table, and this will be a study guide or kind of like a review session for us to answer different questions about Unit 3. So right now, I need you to take out a calculator, a periodic table, a pencil or something to write with, and a notebook or a piece of paper, okay? So pause the video if you need to and make sure you have all these things ready. Now let's start with the mole. That was the first thing that we studied in Unit 3. We're not talking about this mole, of course, we're talking about the mole that we use in chemistry. And a definition for the mole will be the amount of substance containing the same number of units as there are atoms in exactly 12 grams of carbon-12. So this is the proper definition of a mole. And from this we know that 1 mole will always be equal to 6.022 times 10 to the 23rd units, which is Avogadro's number, and 1 mole is also equal to the molar mass of a substance. Now, this will be different for every single substance on Earth, okay? Here we have a picture showing 6 different beakers, and we see that they all contain different substances. Now, all of them contain 1 mole of their own substance. For example, here we have 1 mole of mercury 2 oxide, and here we have 1 mole of sucrose. And it's very easy for us to see that their molar masses will be different, okay? So even though they are 1 mole each, this is 1 mole, this is also 1 mole, the mass will be different for sucrose than for mercury 2 oxide, but something that will be similar will be the number of units of each of these substances within this mole. So here we would have Avogadro's number of units, and here we will also have Avogadro's number of units. So all beakers contain the same number of units within the mole, however, they all have different masses. Now, if you want to remember more things about the mole, remember we watched a video in class. It was a TED Ed. Here's the link. You can copy that into your browser, or you can just do a Google search and search TED Ed the mole, and you'll find the video there. Now, let's think about how big is a mole. Well, we know different examples from the mole song, and here's another example for you. A computer that can count 10 million atoms per second will take 2 billion years to count 1 mole of a substance. Now, I want you to pause the video and try to solve this problem using unit analysis. Suppose that you don't know the amount of years it will take to count 1 mole of a substance. So you start with the only thing you know is that there's a computer that can count 10 million atoms per second, okay? So try to solve this using unit analysis to determine the number of years it will take to count 1 mole of a substance. Okay, so hopefully you were able to do the unit analysis. Let's see how this is solved. We start here with 10 million atoms per second. That's the rate at which this computer is counting. And we want to change the seconds into years. So we start here. Our second step will be to write down how many seconds are in 1 minute. So that's 60 seconds per minute. And then we change the minutes into hours. So here we have 60 minutes in 1 hour. And then we change the hours into days, 24 hours in 1 day. And finally, how many number of days in 1 year. So 365 days in 1 year. And my answer for this, so remember we multiply all the numbers we have on top, divide by the bottom, which is just 1. So our answer will be here, 3.1536 times 10 to the 14 atoms per year. Now, we know that 1 mole has Avogadro's number of atoms. And now that we have this answer here, we can use it to count how many to calculate how many years it will take us. So you see that this unit's atoms per year, I need to flip them so I can cancel the atoms that are in 1 mole of a substance. So I will write here times 1 year divided by 3.1536 times 10 to the 14 atoms. And my answer will be this very large number, which remember that we have to always remember that we have to use sig figs. So if we only had like one sig fig here, so we should probably have just one sig fig in our answer, right? So this will round up to 2 billion years, and that's how long it will take for this computer to count just 1 mole of a substance. So hopefully you got that right. Now let's practice another problem. This time we'll be converting moles to grams or moles to particles or grams to particles. So in this case, we want to know how many molecules there are in 155.9 grams of carbon dioxide, CO2. So again, this is a problem, unit analysis, where we have to convert from grams to molecules. Pause the video, try to solve this problem on your own, and I'll see you in a minute for the answer. Okay, so let's solve this problem together now. We begin with 155.9 grams of carbon dioxide, and we need to change the grams to moles now. Where did this number come from, this 44? So this comes from calculating the molar mass for carbon dioxide. We have one carbon atom, which has this mass, and we have two oxygen atoms. So the mass for oxygen will be 15.9994, but we have two atoms, so we have to multiply this number times 2. So I multiply this times 2, and I add it to the 12 here, and my answer should be 44.0095 grams per mole of carbon dioxide. Okay, so this is how to get the molar mass, and both of these numbers come from the atomic weight on the periodic table. So with my molar mass, I use it here to convert from grams to moles of carbon dioxide. Now see here that my units cancel, grams of carbon dioxide, and then I have to convert the moles to molecules of carbon dioxide. So I will use 1 mole of carbon dioxide has Avogadro's number of molecules of carbon dioxide. So here again, I multiply this number times Avogadro's number divided by the molar mass, and my answer will be this very large number, and we have to take sig figs into account. So 1, 2, 3, 4 sig figs. My answer will have 1, 2, 3, 4 sig figs, so the answer is 2.133 times 10 to the 24 molecules of carbon dioxide. So that's how we solve problems involving mole conversions. Now let's move to electron configurations. Here we have electron configurations for thallium. So go ahead, pause the video, and I need you to write down an electron box diagram, an electron configuration, the shortcut electron configuration, valence configuration, number of valence electrons, and the valence shell orbit or orbitals for thallium. Thallium has an atomic number of 81. So go ahead, pause the video and write these answers down. Okay, so hopefully for the electron box diagram, you got something like this. Now here, first of all, we have to locate where thallium is in the on the periodic table, okay? Okay, so here we have thallium, atomic number 81. And to write down our box diagram, we start here, remember, always move from left to right and always go down. This is the S block. Here we have the P block, then the D block, and then the F block down here with the rare earth metals. So always move from left to right and go from top to bottom, okay? So we have to reach all the way down to number 81. We start with 1s2, 2s2, and then 2p6, and then 3s2, 3p6, 4s2, and then we go here to the transition metals, D block, which begins with number 3. So 3d10, and then 4p6, 5s2, and then 4d10, 5p6, and then 6s2, and then I have to go down to the rare earth metals. So this begins with 4, 4f14, and then I go back here with 5d10, and then 6p1. So here I already got to the point where I wanted to get. So thallium here, 6p1. So if we take a look at our let's go to full screen again. So electron box diagram should look something like this. And we see here that when you are filling this out, remember always apply the Pauli exclusion principle. So up and down, always take up as much space as possible. So up, then double up, down, down, okay? So here the last one is 6p1, so I start here. If I had the next element lead, then I would have 6p2, and the next arrow will go on the second box, and it will be up here, okay? So electron configuration, pretty much like the box diagram, but in this case we have the big number tells me the energy level, then the letter tells me the orbital, and the superscript tells me the number of electrons that I have for each orbital. So hopefully you got something like that. One thing that I want to mention is please follow the order that we have on the periodic table. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d10. So please don't move the 3d10 here. It goes after 4s2, okay? Then we have 4p6, then we have 5s2, then 4d10. So again, this comes after 5s2. It doesn't go before, okay? So please don't write it here. Oh, typo. This should be a 10. Sorry, just got that one. All right, so let's change it right now. This should be a 10, and I think I have it. Okay, so hopefully that's the only typo. Make sure that everything's correct. And then we have the shortcut configuration. So we have to go to the last noble gas before thallium, and that will be xenon. So I write that with brackets, and then after xenon I have 6s2, and then I go down to the 4f14, then I go back to 5d10, and then 6p1. Valence configuration will always be only the S and the P blocks, okay? Those are my valence electrons. That's the outermost energy levels. Here we see that these are the larger numbers. So only 6s2 and 6p1, okay? 4 and 5 are in a lower shell. I mean energy level. So here, this is the valence configuration. Number of valence electrons, 2 plus 1 should be 3. And the valence shell or orbitals that I filled up here will be 6s and 6p, okay? So for valence shell, this is not the configuration, just to know the valence shell, that will be the 6s and the 6p, okay? So here we don't have to write down the number of electrons. So hopefully you got that right. Now let's talk about the periodic table. So the periodic table, there's a lot of information we can get from here. And I'm going to stop